So let's just build the most basic model where we have some component, some species S0 is converted in species S1. For example, this could be, let's say, a simple phosphorylation reactions. Now, if we want to look at the phosphorylation reaction, you could simply say that this reaction has a kinetic of Michaelis-Menten, where there would be another species that we can call it the enzyme. And this is the protein. Let's call this S. Sorry, I'm doing this one, and let's say species S and phosphorylated species SP, and we can say that some arbitrary, sorry about that. Michaelis constant and the Vmax that would be dependent on the concentration of, let's say, K cat times the concentration of the enzyme. Okay. So the first thing to point out that you will see this dotted line appearing as a catalyst for this reaction, because the system has identified the fact that the rate of this reaction is dependent of the enzyme, but the enzyme is neither produced or consumed during that reaction. It acts as a catalyst. So if we run a simple simulation like that, we need to just create a new application and initialize the system with some initial concentration of, let's say, everything is unphosphorylated at time point 0. And let's make this 10 micromolar and have, let's say, 2 micromolar of enzyme available. And if we run a simple simulation, we should look at how these things behave over time. So let's see what else we need to initialize. We have S, and the reaction is K cat, should not be 0, but should be something non-zero, because otherwise nothing happens, right? And what we see is how S is being converted into its phosphorylated species, and if we run this over a longer time period, we will see that the system will equilibrate in this case with everything going in the other state. We could add a dephosphorylation reaction, and then you would have an equilibrium between a kinase and a phosphatase, but I'm not going to make this too complicated right now to move on to spatial modeling. So everything so far is happening in a mixed uniform compartment. But what if this enzyme is only present in some location in the cytosol? and not in another one? And what if they have different mobilities and diffusion rates? Then you will not have uniform concentrations like in this compartmental model, but you would want to see how things behave in a geometrical representation of the cell. So in order to do that, let's go back to our diagram. How do we move from here to a spatially resolved model? So first of all, we need to add some compartments. And we have everything in compartment C0. And we could say add the membrane around it and add another compartment. And now if, let's say, this is the cell and this is the cellular membrane, and this is the extracellular space. So at this point, we have all our reactions happening inside the cytosol, but we have not associated anything with an actual geometry. So the next step would be to make another application where we will create a geometry for it and have the components of the model diffuse or not diffuse, be located uniformly or non-uniformly throughout the cell. So in this other application, we will need to map these compartments not to a single zero-dimensional uniformly concentration compartment, but have a real geometry associated with it. Now, from one important thing, even in the non-spatial model, is the size of the compartments. And as you can see, there are some typical default sizes that are being applied to when you create compartments. The default size of a compartment in the virtual cell is 50,000 microns because it is a size that is similar to a large eukaryotic cell, for example. So it's somewhere in the neighborhood of what you would expect in the biology, but it can be anything, whatever your specification is. So let's add a geometry to this. Let's make a new geometry. And to keep things simple, for now, I'm just going to create a 2D geometry, and then I'm going to show you in a previously built model how things are viewed and run in 3D geometries. But for the purpose of the demo, it's just simpler to keep it as a 2D geometry. And let's say we could use an image-based one. We can use a constructed solid geometry, which is a language sort of from the type of AutoCAD, CAD programs where it can define spheres and cones and whatnot. But this is what you can see as the different types of geometries that you can define in the virtual cell. So we would need to have a subdomain for both the extracellular and intracellular that we can map to. So let's call this, let's add another subdomain. And let's say this would be a circle and with a radius of let's say 3. And copy the expression. Ready? So let's recap what I did, because this is one of the parts that may not be quite as intuitive in the virtual cell. At this point, I just defined a geometry. It's not yet mapped to the compartments in our model. See, there are no lines between them. Let's go back to the definition. In this definition, a 2D geometry will be represented, obviously, as a flat area on your screen. And unlike the standard math coordinates, one thing that I need to point out is that the coordinate system in the virtual cell has 0 and 0 at the top left, not in the center of your image. So if you are used to a Cartesian coordinate system, this can be a little bit confusing. The reason for that is that a lot of the geometries that are created by virtual cell users and have been used in the early years of the virtual cell came from images from the microscope that have been processed, let's say, in Photoshop, and in a canvas on a computer. Typically, you have top left is 0, 0, and as you go down, you increase on the vertical, and go right, you increase on the horizontal. So this is the coordinate system by default. It does not have to be there, because you can change where the origins are. The one thing that you cannot change is the direction. So let's say we want the origin to be here. So if the origin is here, we start with 5 and 5, which may not be what you would expect. Maybe what you would expect is what you would do if you say the origin is -5 and 5. So this is here. Anyway, you see the vertical coordinates will go from -5 to 5. The horizontal will go from -5 to 5. And in our expression in this case, the center of the circle will not be at 3 and 3. And you would have a much simpler expression than this, which would be x squared plus y squared. And z is obviously irrelevant in this case. So the same image as created by the original wizard, but where the coordinates are like this. So I spent probably a little bit too much time on this, but it is really, really important that you can get your head around the coordinate system in the virtual cell that goes left to right for the x-axis as you expect in any other application, but top to bottom on the vertical axis. So one more thing that I want to show here is if I do this, the order of the subdomains is important, because in an analytical geometry, the way you define the compartments is by evaluating whether an expression is true or false and assigning a point in that domain. So the expression 1 equals to true. So if we look at subdomain 0, all points are in subdomain 0, and the processing will never go to the second subdomain. So the order of the subdomains is important. They're evaluated one by one to assign where the points are in which domain. So geometries have domains, the model has compartments. Now we need to connect these two things together, which is the structure mappings. These structures correspond to a domain in the geometry. So I would say that the cell is this brown part, which is subdomain 1, and the extracellular is this, and the interface between them is the cellular membrane. So at this point, we have a second application of the same model with one reaction, two species, where there is a defined two-dimensional geometry with a given size. And we can actually run the same simulation in a geometry where we can create
I
Yes?
cannot hear anything.
I just waited for it to run,
Okay.
but it went behind. The screen went behind, right? So I just ran the simulation. Being a simple system, it runs very quickly. And here, it runs up to a second. And if you move the slider up and down, you will see what happens everywhere. And everything looks gray. And why does everything look gray? Because everything is uniform in concentration. But on the right side panel, you will see that the values are initially, everything is min-max 10. And as you slide down, it goes down this way. And once it has an autocolor system that will do a red to blue mapping of values between the smallest and the highest value. And what you see here are numerical imperfections around the round corners. In reality, everything is still uniform. And if we don't do an auto range, if we do an auto range at all times, this is what you see, because the smallest value is at time point 1, 2.6, and the biggest one is initially at 10. So over time, things go down as expected. And if you want to see how things happen over time in a particular location, you have these little tools here. Let's look at the dot here and plot this over time, and you see the same time course as in the compartmental model. So far, everything recapitulates what we have seen in the compartmental model, because there's nothing that would create anything unhomogeneous in the spatial models. And here comes the important part for spatial modeling. When do we need this? We only need this if there's something that makes things unhomogeneous in your compartments. For example, we could say that the enzyme is only located in the top half. So the enzyme is, right now located everywhere. So how would we do that? Let's go back to the initial conditions. The initial condition is 2 micromolar with no spatial expression associated, but we could say this is times x greater than 0 between parentheses. Again, all expressions are evaluated and inequalities are evaluated as Boolean expressions. So what this means is that the concentration will be 2 micromolar whenever the x coordinate is greater than 0. And let's see how that looks now. If we run this again. Again, it went behind, window went behind. So we were looking at E, and you will see E is 2 on the right hand of our circle and 0 on the left hand. And now you can see that the species is being phosphorylated only on the left-hand side and then moves to the right-hand side. And we initialize the enzyme to the right-hand side, but because it has a non-zero diffusion constant, it will start diffusing over time into the other part of the cell. So let's try and see in these results what happens to 2 points that are located more on the right-hand side of the cell and on the left-hand side of the cell over time. And for the enzyme, which is neither produced nor consumed during the reaction, you will see it starts converging towards the same concentration everywhere because initially everything was on the right-hand side or right half of the cell, but then the diffusion tends to mix it and make it uniform throughout the cell. Our reaction of phosphorylation starts happening faster on the right-hand side, but then it also happens on the left-hand side of the cell. And eventually, everything will become uniform if all 3 species diffuse. So let's run this before we finish. Let's run this for a longer time period. In every 100 milliseconds. Now this takes a little bit longer to run. It's run locally on my computer, on my laptop here. And let's look at the results again. 8 point here, here. As you can see, the enzyme became equal all over the place, equilibrated to an overall concentration of 1 micromolar because it was 2 micromolars in the right half of the cell, 0 in the left half of the cell, just as expected. And our unphosphorylated protein, again, followed the same trajectory as the compartmental one, ending up over 10 seconds, as we've seen in the compartmental model, going down to 0, just with some slight different speeds in the two parts. But what if the enzyme is actually on a cytoskeletal framework and it doesn't diffuse freely? Only the substrate and the phosphorylated substrate diffuse. What happens then? And there is the virtual cell main window. It's here. As a default, so the default diffusion concentration is 10 for all species in the virtual cell, but we can make this 0, so it doesn't diffuse. And then we don't have to set up boundary conditions and all of that. You can read about the boundary conditions at the edge of the computational domain in the tutorial and the manual. But let's just make this not diffuse, and we run this simulation. And behind the window, oops. Which one is it? This one. I already have points on it. Let me just close them and rerun them. This is the old one. Okay. Rerun it. The enzyme at these 2 points stays constant because it doesn't diffuse. But what about the substrate? Now we see a more significant difference between the rate of phosphorylation in one area of the cell versus the other than before, with a continuous gradient until the final uniform concentration that is being maintained across the cell from the right to the left, because we have a non-diffusing enzyme and a diffusing substrate. And you can then experiment further, say, let's do this. If it is a slow diffusing substrate, you will see a bigger gradient, and so on and so on. But I will stop here. There's a lot of things to explore in the spatial simulation domain, including going through 3D geometries, importing images from microscopy data or any other source of real life imaging data, exporting your results in images, movie formats, We could probably spend an entire day and just scratch around the surface about the capabilities of spatial modeling. But these are the basic steps that you need to follow: define a geometry, map things, allocate areas, diffusion reactions, and then start running spatial simulations.
Thank you, Jan. You have a question in the chat about colors within the circle. And
Yes.
so,
Let me look at the chat.
Yeah. So, I mean that colors within the circle depict a gradient. And such gradient is produced. Yeah, so Jan.
Yeah, I can show this again. So this is, the colors are a mapping between the lowest value in the area, which is mapped to blue, to red. It's just a typical heat map coloring. And you can do that against the min and max at all times, or only at the time point at which you are looking. So if I'm looking at this particular time point here, which is at 3.2 seconds from the simulation, you will see higher concentration around here. And if you hover with your mouse, it shows that what value is at what coordinate, and you can make other types of plots. If you, for example, draw a line from here to here, you can plot this as a kymograph and see the concentrations in both 2D and space and time.
Okay, so thank you.